Good morning, students. Students, good morning.
Good morning, sir.
We came late because ray optics is very big topic. So I was like preparing the slides for you. It took very long time. Okay, so let's start now. So what we have to do today? Today we have to start refraction. Reflection we discussed yesterday. Okay, so refraction we are starting today. Refraction. Refraction means is when light is going from one medium to other medium. And when it goes from one medium to other medium, there are certain laws that we follow, and that is Snell's law. So, what Snell's law says, if you're talking about change in medium, the change in medium, basic thing what he said that we are discussing right now. So, here if suppose coefficient of refractive index is mu1 and here coefficient of refractive index is mu2, and if the light ray is going from medium 1 to medium 2, okay, then what will happen? It will deviate from its path. It will be deviating from its path. So, okay, fine. It will deviate from its path. Okay, suppose it went like this. It was coming in this way, it went like this. Then this deviation depends on how much is the coefficient of refractive index of the two medium. Okay, this deviation depends on what is the relation between mu1 and mu2. This is what Snell's law says. And value of this one, he said that if this is angle of incidence and this is angle of refraction, then we can write as mu1 sin I equal to mu2 sin R, or you can say sin I by sin R equal to mu2 by mu1. Okay, now the question comes out, what is this mu1 and mu2, which we are saying coefficient of refractive index. Okay, coefficient of refractive index. Now here we are going to see coefficient of refractive index, which we are representing with mu, right? So this mu is defined as, it is the ratio of the speed of light. So mu is, if suppose mu of the medium or mu in general, mu is actually speed of light in vacuum to speed of light in the medium. Which medium? Whose refractive index is this? Speed of light in medium. Speed of light in medium. Okay. So mu is equal to actually what? C by V. Whose mu is this? Medium's mu is there. Okay. Medium's mu. Mu of medium. Okay. Mu of medium here. What is coefficient of refractive index of vacuum? 1. This is 1. Or air also approximately 1. Approximately 1. Okay. So can we write over here, this is vacuum here? Yes, we can write with respect to vacuum. Because here we are writing speed in vacuum and here we are writing speed in medium. So we can write it like this. What is the meaning of this V mu m? V mu m actually is mu m by mu v. Mu m by mu v equal to C by V. Mu m by mu v equal to C by V. So what we can see from here, that mu is actually inversely proportional to velocity. Mu of medium is there, whereas velocity of the medium is in denominator here. So what we can do, sin I by sin R when we are writing here, sin I by sin R equal to mu2 by mu1, I can at the same time write as v1 by v2. See here. Okay, this is velocity in medium only, no? Vm. So mu m is inversely proportional to Vm. So here also mu2 by mu1 equal to v1 by v2. Okay, now this light is a form of wave. Okay, this is in wave form. So we know that if suppose speed we are talking, then wavelength also we can talk, right? So what relation we have between speed and wavelength? So direct proportionality is there. Why direct proportionality? Because frequency remains constant. Whatever is frequency here, same will be frequency here. Okay, frequency doesn't change with change in medium, right? So that point also we'll write. Frequency doesn't change. Frequency of wave does not change with change in medium. With change in medium. Change in medium. So because of that reason, what happens? Speed is directly proportional to wavelength. So what we can write over here? We can write this as lambda 1 by lambda 2. Lambda 1 by lambda 2. So this is actually the Snell's law. Sin I by sin R equal to mu 2 by mu 1 equal to V1 by V2 equal to lambda 1 by lambda 2. Okay. Now what about the deviation? We are saying that deviation has happened. Yes, deviation has happened. Deviation is how much now? And how it depends, like it's going to go away from the normal or it's going to move towards normal. How we are going to decide? This is there, sin I and sin R are there. Okay, if R is more than I, like in the diagram it is there. So it means is mu 2 is rarer, right? Mu 2 is rarer. We can see that over here. Mu 2 is basically gives us the idea about which medium is denser and which medium is rarer. Which density here? Is it mass density? No. It is the density or the opposition offered to the light. Okay, if it is a denser medium, more opposition to the light is there. If it's rarer medium is there, less opposition to light is there. Right? Say from here we will decide. If suppose mu 2 by mu 1 is smaller, mu 2 by mu 1 is less than 1. Mu 2 is smaller than mu 1. So what will happen in that case? Okay, let's see. Mu 2 smaller than mu 1. If mu 2 is smaller than mu 1, that means mu 2 by mu 1 is less than 1. That means sin I by sin R is less than 1. That means sin I is smaller than sin R. Simple. That means R is greater than I. R is greater than I means is ray, the refracted ray is moving away from the normal. A refracted ray is moving away from normal. Away from normal. Then the other thing also is true. Correct or not? If mu 1 is greater than mu 2, then what will happen? We know that what will happen. If mu 2 is greater than mu 1, right? Then mu 2 by mu 1 is greater than 1. Sin I is greater than sin R. Okay, so that means R is smaller than I, right? So refracted ray will bend towards normal. Bend towards normal. Okay, so this is how it is. Very simple. So when mu 2 is less than mu 1 or mu 2 is greater than mu 1, that means we are entering into denser medium. Here we are going into rarer medium. Mu 2 is less than mu 1 means we are going into rarer medium. Okay. What about deviation now? What about deviation here? You can see that deviation is what? So this is how the ray is coming. Okay. So deviation is this now. It was coming like this, but because of refraction it went like this. So this is delta. This is delta. So how much is delta? We can see that this is I. So this is also I. Okay. Whereas this R. So which is bigger? R is bigger. I is this. So delta is equal to R minus I. In this case, delta is R minus I. In another case, when it goes to denser medium, then delta will be I minus R. Okay. Then it will become I minus R. Right. So this is how Snell's law is defined. Mainly Snell's law is this. Okay, so we should be knowing that the exact value, because they can ask you anything, whether it's in the ratio of coefficient of refractive index or velocity or wavelength. All we should remember. Okay, then what we have? Okay, then as I told you, if we are writing coefficient of refractive index like this, so what is the meaning of this? This means this is mu2 by mu1. This is mu2 by mu1. Suppose we have to write W mu G. That means mu of glass by mu of water. Okay, mu of glass by mu of water. Then G mu W. G mu W will be writing mu W by mu G. And this is actually equal to 1 by W mu G. Okay, now based on this also questions are asked. Right, let's see one question we will solve. So what it says W mu 1 equal to 6, W mu 2 equal to 4, A mu W is 4 by 3, then find A mu 1, A mu 2, 1 mu 2. Okay, so from first information what we are getting, W mu 1 equal to 6. So it means mu 1 by mu W equal to 6. Okay, mu 1 by mu W equal to 6. And already mu W is given because air's refractive index is 1. So you can consider this is mu W only. So mu 1 equal to 6 mu W. So 6 into 4 by 3. What are we getting? 8. So this is mu 1 equal to 8. Same way we can find mu 2. So for mu 2 what we can write here? That's W mu 2 equal to 4. Okay, that means mu 2 by mu W equal to 4. Now mu W we know already 4 by 3. So mu 2 equal to 4 into 4 by 3. That is 16 by 3. Now what the question is asking? Then A mu 1, we got it. This is A mu 1 only. So A mu 1 is 8. Same way A mu 2 is 16 by 3. Okay, then what we have to find? 1 mu 2. So 1 mu 2, actually mu 2 by mu 1. That is 8 by 16, 3. That means how much we are getting? 3 by 2. Okay, so 1 mu 2 is equal to 3 by 2. Right? So this way also questions are asked. So we should know this as well. Now let us see glass slab. In the glass slab, how refraction is happening. This is glass slab, let's see. Suppose its coefficient of refractive index I am taking as mu. Okay. And incident ray is coming in this way. Okay. The normal. This is normal here. And since it's glass slab, so I am considering this to be a denser medium. So what will happen to the ray? It will go towards the normal. So it's going towards the normal, then goes in this way. Now again refraction. So here is normal again. And now where will the ray go? It will go away from the normal because this is rarer medium. So it will go like this. Okay, it will go like this. So what we are getting from here, if suppose this is angle of incidence here, then this is angle of refraction. And since this is normal and this is also normal, both are parallel. So this angle also will become R. And this is E. Okay, that's E. Now if here and here medium is same, let's say this is also air, this is also air, and we apply Snell's law, then what are we getting? If here medium and here medium is same, then angle of emergence will be equal to angle of incidence. Angle of emergence will be equal to angle of incidence. We can see that. Okay. What is Snell's law? Mu 2 by mu 1 equal to sin I by sin R. Mu 2 is what? Mu. Mu 1 is what? Air. Equal to sin I by sin R. At this surface. Now apply at this surface now. What is mu 2 here? this air is mu2. So 1 by mu2 by mu1 equal to sin I. I is what? Sin R by sin E. So sin E equal to mu sin R. Okay, and here sin I equal to mu sin R means sin mu sin R, that means I equal to E. So I will be equal to E if on the two sides we have same medium. That means this ray will be parallel to this. Okay, this will be parallel to this. You can see that. Okay, so both these rays are parallel to each other. Both rays are parallel to each other. Okay, but from here we can see that path, definitely this and this are parallel, but they are not going, or it is not going through the same path through which it was coming. There is definitely some shift is there. Okay, so what is this shift? Shall we find that? Okay, let's find what is the shift. So from here, let's put a perpendicular on that one. Okay, let's put a perpendicular here. Now this one we are going to find. Okay, what is this perpendicular distance? That we are calling as the lateral shift. Okay, let's assume that that is D. Right, so what it is now, let's name it. This is O, let's say this is A, this is B, and thickness of the slab, let's say is T. Okay, now we have to see the triangles here. There is a triangle OAB. In that one only D is there. So this is R, okay, this is I. So I can say this angle here is also I, this. Okay, this is incident ray and this is normal. So this has to be I only. Okay, this angle is I. And this angle is R. This angle is R. So this angle will be what? I minus R. Okay, in triangle OAB only we are seeing. Triangle OAB. So we can write sine of I minus R. This angle, sine of I minus R equal to what? D. D. This is perpendicular, okay? Sine of I minus R is equal to D by this. This is hypotenuse. The hypotenuse is this. What is that? OA. D by OA. Now somehow if we get OA, we will be getting D value also. Now how to get OA? For that we have to see this triangle. Let's say this is M. Okay, so in triangle OMA, what we have? What we require? We require OA. Okay, and this also is right angle triangle. Correct? What is known to us? This side, which is T. This is known to us, this we have to find. So that means cos R we have to use. So cos R equal to T by OA. So OA equal to what? T by cos R. That's all. Our work is over. We wanted D. D is OA into sine of I minus R. D equal to OA into sine of I minus R. So OA value we are writing T by cos R. OA is T by cos R. And that is sine of I minus R. Okay, so this is called lateral shift. This is called lateral shift. Okay, so here and here medium is same. We know that angle of incidence and angle of emergence are equal, but at the same time there is shift in the path of the light, and that is we are calling as lateral shift, and its value is T by cos R into sine of I minus R. Okay, let's see then further. What is this TIR? So before TIR, we should see there is one more type of shift is there in slab. Which shift is there? If suppose the light passes, if suppose we have a slab like this, This is the slab. Okay, its thickness is T. Coefficient of refractive index is mu. Okay, but this one I should do later. Okay, we'll do it later, little later. Once I am going to tell you about apparent depth and all that, after that we'll do. Okay, so let's come on to this one now. What is this? TIR. Okay, now TIR means what? TIR means is when the light has to move from denser to rarer medium. So this is denser here and this is rarer. So when denser to rarer light is moving, it means angle of refraction has to be more than angle of incidence, right? Okay, so in that case, this is, let's assume this is normal. Okay, and this is our first ray, right? So what will happen? As this is incident ray, it will go in the other medium, it will go into the other medium like this. Okay, you can see that angle of refraction is a lot more than angle of incidence. R is greater than I. Now what? We increase the angle of incidence. We made angle of incidence like this. Okay, this angle of incidence. Now because of this, what has happened? Because of this, angle of refraction became maximum. What is the angle of refraction maximum means? It became 90 degrees. Okay, it became 90 degrees. So let's make it with a different color here. Okay, let me make it with red. Okay, so what happened now? Angle of refraction became 90. So it's going like this through the surface. Right. So this is, and this here is 90 degrees. So when angle of incidence for which angle of refraction is 90 is called critical angle. We denote it with critical angle. What is critical angle? Angle of incidence for which angle of refraction is 90. C. C means angle of incidence for which angle of refraction is 90 degrees. Okay, now we are going to increase this angle of incidence further. Okay, we want to increase it more. Then what will happen? Then the ray returns back to the same medium. Okay, it returns back to the same medium, something like this. Okay, so here it's like this. Okay, so here in this case, what we can say, and this is angle of incidence, and this is angle of reflection. This is reflection. So this process we are calling as TIR. This is TIR. So when angle of incidence is more than critical, then the ray returns back to the same medium, and this process we are calling as TIR, and it does follow laws of reflection. TIR is there means it follows laws of reflection. Laws of reflection. That means angle of incidence equal to angle of reflection. Okay, this is there. Now, if suppose that okay, let's find out that we didn't find it. Okay, this is mu1 and this is mu2. So let's find out that what is the critical angle's value. What is critical angle? So we'll say what? Say mu1 sine C. Mu1 sine C equal to mu2 sine R. What is sine R? It is sine 90. For this red light, that only is critical angle, right? So mu1 sine C equal to mu2 here sine 90. what we are getting? Sin C equal to, because this is 90. Let's write it as mu 2 by mu 1. Okay, sin C equal to mu 2 by mu 1, or sin C equal to 1 by mu 1 by mu 2. Correct? Now, how we used to write, let's say 1 mu 2. 1 mu 2 we used to write mu 2 by mu 1. Okay, then 2 mu 1 how to write? Mu 1 by mu 2. So here is what? Mu 1 by mu 2. So what we will write? 1 by 2 mu 1. Now what is mu 1? Remember that from where the ray is coming. That means denser medium's refractive index. 2 means refractive index of rarer medium. Remember that always. Normally mu 2 used to be air. So normally we will be writing here mu 1 only in normal cases. Okay. So remember that from whichever medium the ray is coming, that is mu 1, and where it is going is mu 2. So sin C equal to 1 by mu 1 by mu 2. Clear? Okay, fine. Now let's suppose this is air only. Mu 2 is air. Okay. Assuming mu 2 is air, mu 2 is 1, then sin C is actually equal to 1 by mu 1. Okay. Now suppose C for a medium is very less. C for any medium is less. Okay. So C for a medium is less. It means the ray is going to do TIR very soon. Okay. How? Because we are saying that if C is small, so C is small means is here itself it will be starting doing TIR. With very less value still, it will start doing TIR. What is the meaning of that? Its meaning is that particular medium, okay, that particular medium does not allow the light to go out. It wants to keep the light inside. That means it has got more storage of light. Something like diamond is there. More TIR happens in that. It doesn't allow the light to go out. Maximum light it wants to keep inside. And that's TIR. Okay, so TIR is happening more means that particular medium is not allowing the light to go out. It wants to keep the light inside. Okay, and that is the meaning of TIR. Okay, so this is TIR we saw in terms of mu everything. Right, then we got this relation also that C for any medium is less. Then what happens? Now we will be correlating this with lambda. Okay, now what we know already, what we have studied, we said that mu is inversely proportional to lambda. Mu is inversely proportional to lambda, and sin C is also inversely proportional to mu. So can we say that sin C is directly proportional to lambda? Remember that. Okay, this we have already seen. Sin C is inversely proportional to mu, mu is inversely proportional to lambda, then sin C is proportional to lambda. Correct? And this is one relation we are getting. Okay, so let's see one question based on this. Here is this question. So this is denser medium, this is rarer medium, this is how the light is going. Okay. 3 lights are there, one is green, one is yellow, another one is orange. Okay, and we can see that in this one yellow, okay, is passing through the surface. That means the angle of this yellow one is critical angle, and in fact all 3 are parallel only, right? So for this angle, whatever that angle is critical angle for yellow. A question is asking which ray will undergo TIR. Which ray will undergo TIR? So if suppose this angle is theta here, okay, this is also theta, this is also theta. Which ray will undergo TIR? Yellow is already having critical angle. So what we can say? little while ago we said that sin C is directly proportional to lambda. We saw that proportional to, not equal, proportional to lambda. Okay, all right. Now these are three lights. So we know that if we are going to write the pattern, now in this one we know that red's wavelength is more. So red means this is here is orange, yellow and green. So we can say that lambda value for green is least among them. Then it is yellow and then it is orange. Okay, violet's wavelength used to be least and red's wavelength used to be more, maximum. Okay, so here lambda orange is there, so its wavelength is maximum. Then lambda for Y, then lambda for G. This relation I have, that means I can say C for green color because it's proportional to lambda. So C for green color is least in this particular problem. C for green is least and C for orange is max. So which is going to get total internally reflected? For yellow, if it is critical angle, but critical angle for green is least we are writing. So critical angle for green even will be less than yellow. Yes. So that means green one is going to start totally internal reflection first. So we can make it like this. Okay. It will be coming down. Which color? Green color. So its question's answer is this. Okay. Whereas orange color may be going out. Green will be inside only, orange will be still going out only. So sin C is proportional to lambda. Lambda is less means C is less. C is less means TIR is happening sooner. Okay, let's move forward then. What are the examples that we have for TIR? So one is optical fiber. Optical fiber is what? Optical fiber is a cable. It's a cable and in which the data used to transfer, something like this. Okay. Okay. So this is like a tube and within this data will transfer. Okay. With the help of total internal reflection. Right. Total internal reflection. And it will move with the speed of light. Okay. So if the data is coming in this way, it will be reflected everywhere and it will be moving like this. This is what happens in optical fiber. Okay. So here mu, say mu1 and here is mu2. So which one is denser? Obviously mu1 is denser than mu2. So what we used to do? We used to make sure that this angle here is more than critical. If this is angle of incidence here, this angle will always be more than critical. Because of that, the entire data without any loss will be transferred throughout this optical fiber and we will be getting the data at the other end. Mobile transmission is happening like this only. Whatever the mobile communication is happening, it's happening through optical fiber only. Okay, so this is optical fiber. Then this bulb in lake. Here we can see what's happening, right? So we'll make one lake over here. There's a lake, and suppose bulb is here. This is the bulb. Okay, at what depth we are taking it? Let's say that the depth we are taking here is D. Okay, let's take it as D1. And here, coefficient of refractive index, we'll take mu, and here is air. Okay, so what happens? from here, from the bulb, rays will be going in all the directions, everywhere. Okay. So some of the rays I am making like it's going like this one. Okay. One more. It's going like this. One more I will make going like this. Okay. Now, in all the three, if I am going to make the normal here is also normal. Here also normal you take. Here also normal you take. Now, in three cases where angle of incidence is more, so we can see that continuously angle of incidence is increasing. This angle is smaller, this angle is more, this angle is the max. This angle is the maximum. So, if I assume that here total internal reflection is happening, okay, this is critical and this is more than critical. Okay, so what will happen? Will this light go out? Answer is no, it will not go out, it will return back. Go like this, right? It will be going like this. So, this is TIR. Right. So, which light is going to move out, which is in less than, which is making less than critical angle. This is the surface of the lake, this is the bulb. Okay. So, which light is going to move out, which is making less than critical angle over here. Okay. So, make it how it will be going out. Okay. This one will be going out. Something like this. Okay, in this area, whatever the light is there, that will go out. That means this side also we can make same thing. Yes, we can make same thing. Okay, we can say this is also critical angle. Okay, so like this it is. This is critical. So within the critical, this light will be going out. So suppose that a person is seeing over here, it will find that light is coming through the circle. Kind of a spectacle for him. Okay, so light will be coming out from here. Now, what the question will be asked from you? They'll ask you that what is the radius of this one, or maybe what is the area of this surface from where the light is coming out. So we have to find it. So what shall we do? We know that this is critical angle. If this is critical angle, this is also critical angle. Critical angle's value we'll find. What is that? So mu sin C equal to 1 sin 90. 1 means coefficient of refractive index of air. Okay, coefficient of refractive index of air we are taking as 1. So mu sin C equal to 1 sin 90. So sin C equal to what? 1 by mu. It's 1 by mu. Now what we can do? Now this triangle is here. We can see this triangle here. This triangle. Okay. So in this triangle we can say tan C. Tan C equal to R. Now this is R. Okay. Tan C equal to R by D. Tan C equal to R by D. Sin C value we have, tan C value we have. Can we have the relation between them? Yes, we can have. We can definitely have relation. So from here I can find sin C value also. Sin C value we can write as R by root over R square plus D square. We can do that. Now this value we got, this value and this value I am going to equate. So 1 by mu equal to R by root over R square plus D square. What we want R value. Okay. So square it. Let's say mu square R square equal to R square plus D square. Then R square is here, it is mu square minus 1, that is equal to D square. So R value is coming D by root over mu square minus 1. R equal to D by root over mu square minus 1. Now when this question will be asked from you, they will give you the value of mu and all that. Here we have not taken value, so that's why we have got a kind of formula, but my suggestion is don't remember the formula, see the method. First, calculate sin C value or rather critical angle value, and then see in the triangle what is the relation, and then put the C value. So since you are doing it with the value, you will be getting directly like 30 degree, 40 degree, 45 degree, 60 degrees. Directly you can put it over here and immediately you can get R value. So R value is this. then area is pi r square. Okay, area is pi r square. So that's all. So the light will be coming through this area. Okay. Now this is how we can use TIR relation. Okay. Now what we have, apparent position of object. Apparent position of object means object is in different medium and you are watching from different medium. Okay. Now suppose that this is the object here, same like bulb only. Okay. Distance of bulb from the surface we'll say is d. Okay, this is d. Here you are in mu1 and this is mu2. You are observing from mu2. This is the observer. Okay, so now what will happen? This I'll be making slightly away from the north, slightly away. Here it is. Okay, so now what is happening? This ray, which will go into this one, obviously it will not be going directly. Okay, so what will happen then? In that case, it is going to deviate from its path. I suppose we take one of the ray, which is going out, something like this. Okay, now because of the medium, what will happen? It will deviate from its path. So which light will go to him? Deviated light, obviously. Okay, so what will happen? It will not find the object at the same point, it will find it somewhere else. So what light is going in his eyes? This light is going. Okay, so because of that, what he feels? Light is not coming from here, light is coming from somewhere else. Okay, so according to that fellow, light is coming from this point. Okay, and this point is we are called as apparent position. Apparent position. Okay, so let's say this is x. Okay, let's say this is x, and actual value is what? D. What we have? This is angle of incidence. This is angle of reflection, or rather refraction. Right. So basically, all triangles, what we have to do? This is I, so this is also I. This is R, so this is R. Okay. And suppose this is point A, this is point B, this is O, and this is O dash. Then two triangles are there. What do you say? Tan I equal to AB by D, and same way tan R is equal to AB by X. AB by D and AB by X. Okay, now since this I is very close to the normal, so angles involved will be very less. So what we are saying here, if suppose that I is near normal view, what will happen? I will be very small, so is R. Okay, I and R are small angles. So we can write tan I equal to sin I and tan R equal to sin R. But remember that this is only true when you are talking about near normal view. If it is not near normal, then some values will be given so that we can calculate, we can get the value of this I and R. Once we are getting the value of I and R, then once we get I value from here, then we can put it into sin I and sin R. Why sin I and sin R? Because Snell's law is like that only. So sin I into mu1 equal to sin R into mu2. This is what we have, right? So from here we'll keep it. We are writing sin I equal to tan I, so we can write it over here. AB by D mu1 equal to AB by X into mu2. This AB gets cancelled. So X value we wanted. So what is X value? Just see. X value is D. X value is D mu2 by mu1. Mu2 by mu1, or I will write this as D by mu1 by mu2. That means D by, again one more time, okay, 2 mu1. This is the apparent position of the object. Okay, D by mu1 by mu2. What is mu2? coefficient of refractive index where the ray is going. Mu1 means coefficient of refractive index of the medium from which ray is coming. Okay, so whether you are doing it for apparent height or apparent depth, everywhere you can use this formula. But remember that x is equal to d by mu1 by mu2. Mu1 by mu2. It will help you in getting apparent position, whether it's apparent depth or apparent height. Okay, what it is? D by mu2 by mu1. Normally mu2 will be air, so then there is no problem. Okay, then we can write x is equal to d by mu directly. But if it is not air, then you should remember that. Okay, this is apparent position. So now once you know the apparent position, then we should be doing it for glass slab also. Okay, so here if you can make a place for glass slab, at the top it is there. Okay, so a glass slab. Okay, how much shift is produced by glass slab, that we will see. So if glass slab is here, this is a glass slab. Its thickness is T, coefficient of refractive index is mu, and if here the object is kept, here is object, and viewer is on the other side, or maybe mirror is on the other side, or maybe lens is on the other side. Okay, for them, where will be this object appearing? So object appears slightly closer, and this here is called shift. How much is shift? That shift we should know. That is T into 1 minus 1 by mu. 1 minus 1 by mu. Okay, this formula remember, that is the shift produced by the glass slab. T into 1 minus 1 by mu. Okay, this comes from here only, apparent position. From here to here when the light goes, then apparent position, then from here to here when light goes, again apparent position. We adjust them and we get this value as T into 1 minus 1 by mu. Okay. Alright. See now, a beaker is filled to a height of 20 centimeter with water. For an observer, what height the beaker seems to be filled? Simple question. Okay. So what we have here is, a beaker is filled to a height of 20 centimeter. An observer is watching from the top. So for observer, what is the height to which it is filled? That means he is asking apparent depth. Actual depth is 20 centimeter. He is asking apparent depth from us. What is the formula? X equal to D by mu2 by mu1. Am I correct? This was the formula, or mu1 by mu2 was the formula. Mu1 by mu2 was the formula. Okay, what is D? 20 centimeter. Mu1 means what you are seeing? The base of that bucket. Okay, base of the beaker. So base of the beaker is in water. From water it is going to air. So what is mu1? Water. Mu W by mu air. So 20 by 4 by 3 by 1. 1 I am not writing. So what we are getting? We are getting 15 centimeters. For that person, it will appear to be like the base of that beaker is 15 centimeters. Okay. Alright, let's move ahead. A bubble when seen from left means here. Bubble when seen from left appears at 4 centimeter. Okay. And from right it appears at 6 centimeter. What is the thickness of the slab? So that means apparent position from here also and from here also, both we have to calculate. And actual distance we do not know. We don't know actual distance. Or D I will write, right? D. Okay, fine. So what we know? We know that X equal to D by mu1 by mu2. X is given to you as 4. D we don't know. Mu1 is 2 and mu2 is air. From here light is coming to this. So D by 2 equal to 4, that means D equal to 8. Now from right, okay, let's assume this is d dash. Okay, now from the right side it is given that it appears at 6 centimeters. So I am saying y is the apparent position. So y equal to d dash, again mu1 by mu2. So 6 equal to d dash by 2 by 1. So d dash is equal to 12. So what is the thickness of the slab? 12 plus 8, that is 20 centimeters. Okay, thickness of slab d dash plus d, that is 20 centimeters. Right? Okay. A microscope is focused at a spot on the table. A glass slab of thickness 3 centimeters placed on it. How much microscope is moved to keep the spot on the focus? Okay, fine. So this is the table. Okay, and this is the spot. Microscope is focused on this one. Right, now what you did, you kept a glass slab over it. Right, now there is a glass slab of thickness 3 centimeters. And coefficient of refractive index 1.5. Right, now microscope want to focus this once more. So where he should focus, where microscope should focus, and what should be the shift. Okay, so let's see then. Now this is the object, actual position is 3 and this light has to go out, that's all. Okay, so apparent position is what? The apparent position is actual position by again mu1 by mu2. What is d? 3. Mu1 is what? 1.5. Mu2 is 1. So x is 2 centimeters. That means this spot will not appear here. It will appear slightly above. Remember always this apparent position that comes, it comes always from the surface, from where the refraction is happening. Don't take it from here. Where is the refraction happening? This is the refracting surface. Okay, so from here this is 3, now this is 2. So how much shift will be there in the position of the microscope, or rather microscope has to focus which position? This position. So how much it has shifted? 1 centimeter. The shift is 1 centimeter. Microscope has to shift its focus by 1 centimeter. Okay, then refraction at curved surface. Okay, so first we'll talk about single surface. Single surface is like this. This is concave. Okay, this is concave surface, and then similarly will be convex surface also. Convex surface will be like this. Okay, principal axis here. Principal axis here. Right, now its center of curvature will be where? Here will be its center of curvature, this side. And its center of curvature will be this side. This coefficient of refractive index, this medium is mu1. Here we will keep the object, or from here the light will be going. Same way, this is mu1, this is mu2. Okay, we are not deriving anything, we are directly writing formula. Okay, the coefficient of refractive indexes we have written, and we are writing the formula for curved surface. So what is the formula? Mu2 by v minus mu1 by u equal to mu2 minus mu1 by r. And this is just formula, like 1 by f equal to 1 by v plus 1 by u we saw in mirror. Same way, this is the formula. Without any sign convention, formulas are there. Sign convention you have to use. What is the sign convention? Same way, if you are moving in the direction of light, if the measurement is taken in the direction of light, it's positive. If you are taking it opposite, it is negative. Okay, so no change as far as formulas are concerned. Okay, so these are how the two refractive surfaces are. What surface is this? As I said, this is concave. and this surface is convex. Concave means diverging surface and convex means converging surface. Okay, it's like this. Then what we have, directly we'll do the question. Okay, so here this is object here. Okay, this is the medium and it has to go out to the air. Okay, this is the object, center of curvature is given, it is at 20, object distance is 15, and we have to find where is the position of object as seen by the observer. Very simple question, formula based, mu2 by v minus mu1 by u equal to mu2 minus mu1 by r. What is mu2? Air. Air means 1. V value we are finding. Minus mu1. mu1 is 2. Now u value. Now where is the origin or pole? This is pole. So this is on the left side. Light is going obviously from the object in this way. And to measure it, you are coming left from 0. So left from 0 means negative. So this is negative. Mu2, 1, mu1, 2, r. R again is on the left. So minus 2. Right. So what we are getting? 1 by v equal to, this is plus. So it will go here and become minus. Minus 2 by 15. Then this is minus 1 by minus 20. So plus 1 by 20. Okay, that's 60 here. Minus 8 plus 3 equal to 1 by v. Okay, so v is coming minus 60 by 5, that is minus 12. That means on from here left side. So somewhere here will be coming, no, where it is coming 12, yes. So this is image. Image will be here. Okay. So this way we can find from the curved surface. Okay, with the curved surface formula, we can also calculate apparent position. That is also possible. Okay, so far what we saw, glass slab. If you go back, where is apparent position question? Here. Okay, so apparent position means this is plane surface. If we are going to use curved surface formula in that one, what is the curved surface formula? Mu2 by v minus mu1 by u equal to mu2 minus mu1 by r. Now for plane surface, radius becomes infinite. Radius is infinite. So what we have now? Mu2 by v minus or equal to mu1 by u. Now u means is actual position, like d, and v means is x. So what we are getting? Same thing, x equal to mu2 d by mu1. So from here also, if you want, you can use the same formula. See, same thing only. X equal to mu2 d by mu1. If you don't want to remember this formula also, then curved surface formula we can use to get the same answer. Okay. Alright. Then one more question is here. Find depth of bubble as seen by the observer. Where is the observer? Observer will be here. Okay. So one more time. Mu2 by v minus mu1 by u equal to mu2 minus mu1 by r. What is mu2? Again air. So 1 by v. Mu1 is 1.5 by u. Okay, now object is this. Light is going in this way and this is pole. So to measure this 8 centimeter, you are coming down. That means you are moving opposite to the direction of light. That means you will be negative again. So minus 8. Mu2 1 minus 1.5. Again r is negative, minus 5. Okay, so 1 by v equal to This is plus here, so we'll go that side, minus 1.5 by 8. Here is what? Minus 0.5 by minus 20. So plus 1 by 40. Okay, we calculate this one. LCM is 40 only. So this is 85, just so minus 7.5 plus 1. Okay, so V value is coming 40 by minus 6.5. Okay, this is 40. Okay, I think calculation is correct only, 40 by 6.5. Yeah. Okay, so that means V will be here only, down this side. Okay, somewhere here. Alright, then lens. Lens means what? You have two refractive surfaces. Two refractive surfaces we have. Okay, normally we'll talk about biconvex lens. Biconvex lens means is both are convex, both surfaces are convex. Or we talk about plano-convex. Okay, mostly we'll talk about this. Or biconcave, or plano-concave. Very rarely we'll be talking about the third type of lens. Either you say is concavo-convex or you can say is convexo-concave. Okay, so concavo-convex. Okay, concavo-convex. Then convexo-concave. These are the types. Okay, so these types of lenses we use less. Mostly we'll talk about these four types: biconvex, plano-convex, biconcave, plano-concave. So two refractive surfaces they have. If we look at them, we look at biconvex. Okay, now this is first surface. Okay, this is first and this is second. Okay, the second one center of curvature is here and first one center of curvature is here. This is R1. Okay, and this is R2. Okay, this is R1 and this is R2. And coefficient of refractive index, because we are going to talk about thin lens mostly. What type of lenses are there? These are thin lenses. Okay, so these are thin lenses for us. So since radius of curvatures are 2 in this case, right, on one on either side. So in this one, we are going to get focal lengths also 2, one on either sides. Okay, two focuses we will be having. It's not in this one. In single curved surface also we were having two focuses, but it's not required at the moment because normally it is not in our syllabus also. But here, yes, do we have two focuses we will be getting. Right. So this is how we will be using the normal diagram to show that how these are center of curvatures. Now let's go for the lens maker's formula. What this is? Lens maker's formula, it is 1 by f equal to 1 mu 2 minus 1 by r1 minus 1 by r2. Again, this is without sign convention. We have to consider sign convention when we use it. 1 by f equal to 1 mu 2. Now 1 mu 2 means what? This is mu 2, this is mu 1 and this is also mu 1. So this is mu 2 by mu 1, right? Mu 2 by mu 1 minus 1 into 1 by r1 minus 1 by r2, and that is also equal to 1 by v minus 1 by lens formula. This is lens maker's formula, this is lens formula. Okay, so 1 by f equal to 1 mu 2 minus 1 into 1 by r1 minus 1 by r2. Now when I am going to use it for biconvex, suppose I am using it. So 1 by f equal to 1 mu 2 minus 1. Then 1 by r1. Where is R1? R1 is this. Light is coming from this. So is R1 positive? Answer is yes, R1 is positive. So 1 by R1 minus. Then R2. Now where is R2? This is R. Now what about R2? Positive, negative? It's negative. So 1 by minus R. So focal length of convex will be coming positive. Same way focal length of concave will be coming negative. This is the convention. Okay. Focal length of convex positive, focal length of concave negative. Alright. Then power of lens. What is power of lens? Power means is how much a lens can converge or diverge, and it is actually equal to 1 by f in meter. 1 by f in meter. Okay. Same way power of mirrors, curved mirrors. Okay. Power of curved mirrors. What is that? It is minus 1 by f. Okay. In meter. So for mirror, power is minus 1 by f, and for lens, this is for lens, it is 1 by f. Remember that. Clear? Okay. Ray diagrams. The ray diagrams we have to make. Okay. So we will try to make ray diagrams. It's actually difficult, right? Okay, we'll try, but small way we'll try. Okay. Here also, how many we have to make? Object at infinity, object is beyond C, object is C, object between C and F, object is at focus, and object is between focus and pole. Okay. Alright. So here we are doing it for equiconvex lens. Equiconvex lens means is R1 equal to R2. Now remember that this is thin lens. So thin lens, we will show refraction right from the middle only. We are not going to show it that from this first surface, this is the refraction, and then the refraction is from the second surface. Directly we will show it from the center surface only, from this line. That's why this middle line we have made. Okay. Now, first one is what? U is at infinity. So when minus infinity. So when the object is at infinity, its image forms at focus. We know that. That's the convention. Okay. Which focus? But focus is on both sides. So here is f, here is 2f. Same way left side also focus is there, and 2f is also there. Okay. So when ray is coming from infinity, what we will say? That it's coming parallel to principal axis. So it is coming parallel to principal axis like this. Then it must pass through the focus. Okay, it's like this. Then same way one more we will make. Here it is. Then it must pass through the focus obviously. Right. So this is the first case. Here is what image you are getting. Okay. What type of image we are getting? Very small image. Diminished image. Okay. Small means diminished only. Okay. Diminished, inverted, real. Because the reflected rays are actually meeting. So it's a real one. Okay. Next one what? Next one we want to keep U as between infinity and 2f. So minus infinity is greater than U is greater than 2f. Okay, fine. So this lens, I should have copied it. Okay, this time we'll try to copy that so that we are not making it again and again. Okay, so here is your lens. Okay, let's see if we can copy this. Yes. So we'll make it everywhere now. Oh, this full diagram is coming. like this if we try. Yes, that's okay. Okay. Somewhat our effort has become less and it has become little faster. Okay. Alright. But still we have to show here there is F and here is 2F. Same way here is also F and there is 2F. So where is the object we are keeping now? We are keeping the object. We are keeping the object beyond 2F. Okay. Then ray parallel to principal axis, and here also with middle line we have to keep first. Middle line. Okay. Right. So one line parallel to principal axis. Then it will pass through focus. Like this. Then other one what we will do? Other one we will take. It's our wish whether we want to take it from focus or we want to take it from pole. It's our wish. So if suppose we are going from focus here, then the line which is passing from focus will become parallel to principal axis after refraction. Okay. So it goes like this. In this way. Okay. So what are we getting over here? Image is coming here. This is the image. Okay. Like this is the image. So what we can say, diminished image, inverted image, real image. Then at 2F, image will also form at 2F. Where will be the difference then? Difference will come only in the final image, because always remember, convex lens is very similar to concave mirror because both are converging. Same way, convex mirror and concave lens has similarity because both are divergent. Okay. So here again, F and 2F, same way here also. This is F and here is 2F. Okay, I am making directly, okay. It does not take much of the time. It's going like this and then it will go in this way. Then here it will be, and then it will be going like this. So image will format 2F. Okay, same size image. Here is same size image will come. Then what we have taken over here, here is U equal to 2F. Right, then U is less than 2F but greater than F. So between F and 2F you want to keep. So F is here, 2F is here, same way F is here, 2F is here. Why these ray diagrams become important? Because these are the basics. That's why I am making it one more time. Otherwise I could have skipped. Okay. So these are important. This gives lot of information. Okay. So it's here. Then make the center line. Alright. So here is the straight line. It will pass through focus. Go like this, and then another one we will take from pole itself. Okay. So we take from pole. Where are they meeting? Here like this. Okay. So image is forming here. Image is forming here. Like this. This is image. Like this image is forming. Okay, so what we can say about this image? We can say that this image is bigger one as compared to object and inverted so far. Okay. Magnified image, real, inverted. Now what is the next point? Next point is F. Now when image is kept at F, we know that rather object is kept at F, image will go at infinity. We know that, so I am not making this at least. Now U is less than F. Okay, here what we are going to get? We are going to get virtual image. But why this is important for us? Because in concave mirror we saw that the virtual image was forming on the other side. But this is lens. So here where it will be? Let's see. F here, 2F, F and 2F. Where is the object we are keeping? Here. Okay, this is the object. Then center line. Okay, then make one line parallel to principal axis first. Then it must pass through the focus. Okay, another one. We'll take it from pole. Going like this. Are they going to meet this side? And answer is no. So let's take it back side and see what's happening. Okay, so we are going to take them back. So let's see this. Okay, we have taken it like this. Now let's take this. Are they meeting? Yes, they are meeting here. This is the meeting point. This is the meeting point here. Okay, and how is the image? Now image you can see is on the same side as that of the object. Okay, same side as of the object, and in this case it's enlarged image. What type of image it is? Magnified. Virtual, magnified. In concave mirror also we saw the same. Okay, virtual, erect, magnified. So this we will remember. When we are talking about real images, you are getting diminished images also and magnified images also. But when we are talking about virtual image, it is only magnified. Clear? Okay. This is ray diagram. In concave lens, you are going to get always virtual images only for real object, and always it will be small, just like what we used to have in convex mirror. Okay, so I am not making magnification. Now magnification is what? Magnification is always height of image to height of object. Height of image to height of object, right? Okay. What we used to get in lens, we got in mirror we said minus V by U. Here it is plus V by U. Plus V by U in the case of lenses. But if suppose I say for real image and real object, then magnification is positive or negative? Negative. M is negative. Okay. For virtual image, real object, magnification is positive. Virtual image and real object, M is positive. Remember that. That's it. Virtual objects, we are not talking much. Virtual objects, question also are not asked. So forget about virtual object. Real object only we concentrate. Okay. Alright. Questions I am not doing on magnification. Same type of questions are there what we did in mirror. Same type of questions are there in lenses also. Okay. Then focal length on changing the medium. So change in medium, what we have is 1 by f equal to mu2 by mu1 minus 1 1 by R1 minus 1 by R2. Now, which medium are we going to change? Outside medium, obviously. So, if this is a lens, its on medium we are writing as mu2 and outside medium is we are writing mu1. So, if mu1 we are changing, then obviously focal length is going to change. Now, see what is going to happen. If suppose we say mu2 is 3 by 2, mu2 is 3 by 2 and mu1 is 4 by 3. That means I am saying mu2 is greater than mu1. So, if mu2 is greater than mu1, what is going to happen? Okay. And this is which type of lens I have made? Convex lens. So, 1 by f equal to 3 by 2 by 4 by 3 minus 1. And suppose it is equiconvex lens. This is 1 by r minus, this is r2. Okay, if you remember the sign convention, how we showed you when we are talking about lens, where it is here. What I told you for biconvex lens, 1 by r1 minus 1 by r2, because r2 is this side. Okay, the same thing if I am going to do here, this is r2, r2's value is also r, but what I will write? 1 by minus r. What we are getting? 3 by 2 by 4 by 3, that is 9 by 8. So 1 by f equal to 9 by 8 minus 1 into 2 by r. So what I am trying to tell you is focal length is coming positive. It will remain convex. Okay, it is convex. It is convex. But if suppose that mu1 I am going to make bigger than mu2. Now suppose mu2 is 3 by 2, whereas mu1 is 2. Now what is the focal length? Just check. 3 by 2 minus 1 into 2 by r. What 2 by r? This is 2 by r. Now what's going to become? This is 3 by 4 minus 1 into 2 by r. What's going to come? It's minus 1 by 4. Minus 1 by 4 into 2 by r. That means focal length has become negative. Now it has become concave because its focal length is negative, whereas here what it was? Convex. So if you are going to change the medium and outside medium is more denser, then the property of the lens is going to change. If suppose this was concave, so here its focal length would have become negative and here its focal length would have become positive. So concave changes into convex and convex becomes concave if outside medium is more denser. Okay. Silvering of lens. Now silvering means what? Silvering means is one of the surface of the lens you are going to silver. What's this? We have silvered it. Okay, so what will happen in this case? We are changing the characteristic of the lens. Now we are trying to make it as a mirror. This will act like a mirror. But if the ray which is going to come into that one, the ray is coming, what will happen? It will be refracted from first surface. Okay, then it will be reflected from here. Then again it will be refracted from here. So two refractions and one reflection is happening. So in this case we say that power of combination. Why combination now here? Because this is a mirror. So we call it as, it is actually 2 times power of lens plus power of mirror. 2 times power of lens plus power of mirror. Okay. So now what we have to do? We have to find its focal length or we have to find its power. Suppose this is equiconvex lens. Okay, this is mu and this is air. So let's find out its power. Okay, let's find out its power. So what do you say? Power of lens means 2 into 1 by focal length of lens. And power of mirror will say minus 1 by focal length of mirror. Correct or not? Focal length of lens is what? 1 by f equal to mu minus 1 into 2 by r. We saw little while ago. Directly I am writing. 2 into mu minus 1 into 2 by r. And focal length of mirror is what? Focal length of mirror is r by 2. Focal length of mirror is r by 2. So we'll be writing it here. Now, just forget about this minus and all that, okay? Just forget it, everything over here. Just do the plus only. Forget this. Okay, so 2 into mu minus 1 into 2 by r plus 2 by r. So 2 into mu minus 1 into 2 by r plus 2 by r. That is what? Power. Power of combination. What we are getting? Correct only, no? Yeah. So 4 by r into mu minus 1 plus 2 by r. Now 2 by r we can take common from here. So 2 mu minus 2 plus 1. So 2 by r into 2 mu minus 1. This is the power of the combination. Now combination has become what? It is a mirror, remember that. So here you write it minus 1 by focal length of mirror. And this is the focal length of mirror. Then we can solve it like a mirror only. Mirror formula we will use 1 by f equal to 1 by v plus 1 by u. If the question is asked from us, object distance given and he is asking where will be the image, then use mirror formula and get it. This is mirror's focal length. Okay. One more question we will solve in this one. We did it for equiconvex. Okay. Let's do it for let's say plano-convex. Plano-convex is rather easy because one surface is actually plane. Okay. So which one we are going to polish? This plane only will polish. Okay, this is me. Okay. So power of combination again 2 times power of lens plus power of mirror. There is no change in that. So here 2 mu minus 1, 1 by r1. Now this is r1, okay. This is r1 and this is r2. This is first surface. Alright, so then what? 2 into mu minus 1 into 1 by r1 minus 1 by r2. R2 is infinite. It's a plane surface. So I am not writing it. Okay, write it. Okay. Alright. So in this one R1 is going to be positive or negative. Light will be coming like this. This will be the object side. Light is coming like this. Okay. Then this surface is here. So where is center of curvature? This side. And this is R1. This is pole. So R1 is positive. Left side. In the direction of light. Okay. This is the pole. This is origin. So to measure R1, how you will go? Like this only. So it's positive. That's why I have written positive. So 1 by R1 minus 1 by infinity. And power of the mirror is also 0 because it's a plane surface, plane mirror. So then this is it, 2 by R1 into mu minus 1. This is also mirror, yes, minus 1 by focal length. One more question you can solve because this is a different kind of a thing. Should not get confused. Okay, you can do it with the concave one. This is concave. Polish this one. This is mu. Equiconcave will take. Okay, this is R1, this is R2. First surface, second surface. So again, power of combination. 2 times power of lens plus power of mirror. 2 into mu minus 1 into 1 by R1. Now, this is R1 and its center of curvature is this side. Light is going in this way. So how you are coming? This is origin. You are coming on this side to measure R1. So that means negative. minus 1 by R2. R2 is positive. Then plus power of the mirror. Power of the mirror will be 1 by F. 1 by F is R by 2. So here's 2 by R. Okay. Here is 2 into mu minus 1 into minus 2 by R, and here is plus 2 by R. 2 by R you have taken common. 2 mu minus 1. No. Minus 2 mu plus 1 plus 1. This is 1 by focal length of the mirror minus. I hope I have done correct. 2 by R I have taken common. So minus 2 mu plus 2. Okay. Minus 2 mu plus 2. And here is also plus 1. Now it's correct. Okay. So this way we can find for equiconcave. Okay. Silvering of lens. Now combination of lens. If two lenses are in combination, lens number 1, lens number 2, then power of combination will be what? P1 plus P2. Focal length terms 1 by F1 plus 1 by F. That's equal to 1 by F. That depends. If suppose one is positive, one is negative, you have to use sign convention. Okay. If suppose little gap is there between the two, then small gap, not large gap. And this is X. Now in this case, we write as P is equal to P1 plus P2 minus D or X P1 P2. Okay, P1 plus P2 minus X P1 P2. Remember this formula. Both. See, power of the combination question is there. One is convex lens, other one is concave. It is given to us. What is power of combination? Simple question. So what's coming? Nothing is there in it. Very simple. P equal to P1 plus P2. So this is 3D and this is 5D. So answer is minus 2D. That means combination is going to be a concave one, a concave lens. Okay, combination is going to be a concave lens. Okay. Next, this is interesting. Now, two convex lenses are there. In between, water is there. So there are three lenses. 1, 2, 3. We have to find its combinations, focal length. Okay. So what we have here, P equal to P1 plus P2 plus P3, or 1 by F equal to 1 by F1 plus 1 by F2 plus 1 by F. Now, good thing about this is, like first one and this one, these two lenses, these convex lenses, they are similar. That means 1 by F1 and 1 by F3 are same. So what we can do, we can write this as 2 by F1 plus 1 by F2. Let's write 2 mu minus 1. What is that mu? 3 by 2 into 2 by R. Directly I am writing because R1 and R2 both are given same. Okay, convex lens we add like this. Now concave. So what is mu here? 4 by 3. So 4 by 3 minus 1. Mu minus 1 again. Mu dash minus 1 into what? Now its surface is this one and second surface is this one. So in concave, we write this minus 2 by R. Okay, put the value. Anything we can take common. 2 by R is coming common. So take it. Okay, 2 by R is common. Now what is 2 mu minus 1? So 2 mu minus 2. 2 into 3 by 2 minus 2. Okay, 2 into 3 by 2 minus 2. Now here plus or minus because of this minus. Mu dash is 4 by 3 minus. Okay, so this here is 2 and 2 gets cancelled. 3 minus 2 is 1. So it is actually 1 by f equal to 2 by 20 centimeter. This is 1. Now minus 4 by 3 minus 1, that means 1 by 3. So 1 by 10 minus 1 by 3, that means it's going to be a concave lens because focal length is coming negative. So this will be what, 30? 3 minus 10. So focal length is minus 30 by 7. It's a concave lens. Okay. So this way, this is type of questions are asked. Okay. Cutting of lens. You want to cut the lens. Okay, fine. Fine. So there are two ways in which we can cut the lens. How? One, like this. Okay, cut it like this, and then we get two lenses after that. How are those? They becomes plano-convex, like this or like this. What happens? Now, if suppose that here its power is P, and here power will be what? P by 2. Here is power P by 2. Because one surface you have removed, which were actually refracting it, which are going to converge or diverge it. Okay, because this is curved surface, it's either going to converge or diverge. Earlier two surfaces were there, we were getting power P, now one surface is there, the power became P by 2, P by 2, P by 2. Power became half means focal length has become double. If here is focal length F, then here focal length is double. Okay, focal length has double. Okay, another way how we can cut? Another way we can cut from the middle like this. So what you'll be getting after that? We'll be getting again two lenses. One is this, another one is this. So its power is P and focal length is F. So here is also power is same and focal length is same. No change in power and focal. Then what has changed? What actually has changed? Said intensity. If here intensity of image is I, intensity of image is I here, then here intensity is going to be I by 2. And here also I by 2. Why? Because from this lens, if suppose that when the rays are coming, okay, suppose that 20 rays were passing like this. So from here how much will pass? 10. 10 incident rays only will pass. So that will create the intensity. Here intensity was created by I, was created as I, here it will be obviously half of that. So intensity will become half. Okay. Alright, covering of lens. Now suppose there is a lens here and this below lens we have covered. Covered means is putting a black cloth on this one. How to show you? I'll make it with this gray. Okay, this is gray. Gray will put it. We covered the half portion. What will happen then? Is focus change? No. Power change? No. Power is same P. Focus is same F, or rather focus is same F. P, F remains same. Then what has changed? Intensity. Intensity of image is decreased. Intensity of image is decreased. Okay, I suppose the same lens, we are making certain parts. Okay, now in this one what part is there? This one suppose we covered up. This one also we covered up. This one also we covered up. Now what will happen to power and focus? No change. Power and focus is still same. What is changing? Only intensity is changing. Earlier one image was there. Now how many images? One image only. Why there will be two images? Same. Even if one portion of this one is open, it will be able to make the image, and it will make the image at the same place. If suppose you are going to make it's entirely different, this is mu1, this is mu2, this is mu3, this is mu4, this is mu5, this is mu6, then you can say 6 images are there. But if you are blocking this one, and blocking this one, only open is these 3, then they will make the image at the same place as when it was totally open. There will be no change. Okay, because still incident rays are going in the same way, they will be refracted in the same way, they will be meeting at the same point, there will be image. Only thing is, now you are allowing less amount of incident rays, so intensity is going to decrease. Okay, intensity changes. Nothing else is the change. This is the covering. Our heading is covering, not that you are going to change the coefficient of refractive indices. Okay. So intensity changes. Okay. Okay, see the question on intensity now. Intensity of image through lens is I naught. Through this lens, image is I naught, intensity is I naught. If it is half covered, that means you are covering it half. How to do it? Okay. So you covered it half, like this. And what the question is asking? Question is asking what intensity will be obtained. Now intensity, always remember, is proportional to aperture square. Intensity is proportional to aperture square. Aperture is what? Diameter of the lens. So half you covered up. That means half of the aperture is gone. A by 2. So we will say that how much intensity you have blocked then? The intensity blocked is proportional to A by 2 whole square. That means A square by 4. Earlier, how much was the intensity which was going earlier initially? Proportional to total amplitude, total aperture. So intensity obtained initially, that is proportional to A square, and this is what we are calling as I naught. Here you have blocked. How much you have blocked? Proportional to A square by 4. That means how much you blocked actually? I naught by 4. So how much intensity we are getting? Intensity received, I naught minus blocked. So how much intensity we are receiving now? 3 I naught by 4. Okay, we are receiving how much intensity now? 3 I naught by 4. Right? Okay. Then we want to finish it. How much is the time now? 8 already. It's already 8. Okay. Let's see prism. Prism is what? We have two refractive surfaces again. But,
sir,
yeah.
Sir, I want to go to school, sir, today.
You are going to school today?
Yes, sir, I will see a recording, sir, no problem.
Okay. Okay, fine.
Yes, sir, bye.
So, two curved surfaces are there in prism also. So, here is the prism. Okay, but curved surfaces, this is also having two refractive surfaces, but the surfaces are not curved. These are plane surfaces. Whereas in lenses, we were having curved surfaces. That is the difference. But we often say that thin lens is made from prisms only. Thin lens is actually made from prisms. How? See, if this is the lens, then check here. Okay, this is the prism. Small prisms are there. Okay, where we can say that the surfaces are straight. Small prisms. So you will be making small prisms, and thin prism basically is made from prisms. Okay. Alright, so this is prism over here. This is the first surface. This is second surface. Okay, this is called angle of prism. Angle of prism is between two refractive surfaces. Okay, then this is incident one, incident ray. Let's make one normal here. Okay, then a refracted ray, one more normal. Doesn't look like normal here. Okay, alright, this is normal here, and then ray goes out. This is angle of emergence, this is angle of incidence, this is angle of refraction, this is angle of refraction. Okay, then what? Then deviation. Deviation means angle of deviation is the angle between incident ray and emergent ray. So this is incident ray. Okay, this is emergent ray. Right. So this is angle of deviation. Okay. So we need to have certain relations. What relations are there? A is actually equal to R1 plus R2. A is equal to R1 plus R2 and delta equal to I plus E minus A. These are two very, very important relations that we should remember. A equal to R1 plus R2 and delta equal to I plus E minus A. Okay. Then what? We will use now prism in different cases. What two cases are there? One important case is there of minimum deviation. Okay. Minimum deviation. Minimum deviation we will see here. What is minimum deviation? So minimum deviations case, we make a graph between delta and I. Okay. We make a graph between delta and I. Here is the graph. Okay. Here is delta and here is I. So when I is very less, something like 0, then delta value is also maximum. Okay. Delta value is maximum. Then wait a second. Something it's blur. Are you able to see it clearly? Screen? Slightly blur, right? Okay, wait a second. I think it has become hot or something like that. Okay, we'll finish it. Okay. So this is delta and this is I. So delta value will be more. When I value is less, delta value will be more. But as you are going to increase I value, delta is going to decrease. Okay. Then after that, we will get a minimum value, and once we are increasing I, again delta starts increasing. It will go like this. So this is delta minimum. Okay, and where this delta minimum happens, where I is actually equal to E. So delta minimum takes place when angle of incidence and angle of emergence are equal. So when angle of incidence and emergence are equal, it means R1 is also equal to R2. Why? Because if you are writing Snell's law here, what you will be writing? Suppose its medium's coefficient of refractive index is mu. So we will write here 1 sin I equal to mu sin R1. And when we write it over here, it is mu sin R2 equal to 1 sin E. So we are saying 1 sin E and 1 sin I are equal, then it will be R1 equal to R2. So here R1 equal to R2 as well. So when we are talking about minimum deviation, I is equal to E and R1 equal to R2. Okay. Alright. So then delta minimum is what then? The delta minimum formula that we get. Okay. Delta minimum we get is, we said that delta is already what? I plus E minus A. So it will become 2I minus A. And what is here? We said R1 and R2 both are equal. So A will be equal to 2R1. That is R1 will be equal to A by 2. So for minimum deviations case, mu value we write as sine of A plus delta minimum by 2 by sine A by 2. From where this is coming? Nothing. We are just placing it over here. Sine I value we got from here. A will be here by 2. So A plus delta minimum by 2 is I value and R1 value is A by 2. So this is the condition of minimum deviation. Okay. So we close here today. Okay, because even the focus is also we are losing. Okay. So we'll close it here. I'm giving you this QR code, scan it. Tomorrow we'll start from here, and along with that now we'll be moving into wave optics immediately. Okay. So scan the QR code so that you can read the notes.